Good afternoon, everyone. I hope I'm audible to you. Am I audible?
Yes, you are audible, sir.
Yeah, that's great. I'll just get my notes open. Can you
Yes,
just
sir.
make me the co-host because I want to share the iPad. Let me just check. Yeah, yeah, I think my screen is visible. Yes. So can we start?
Yes, sir, you can start.
Yes, yes. So good afternoon, everybody. Warm welcome to all of you for this live session for this course on linear algebra through uh, geometry. Uh, so, uh, so what we'll do is we will just look at the assignments in the first place. If there are any questions, I'm ready to take the questions. Otherwise, we will start with looking at the assignments, if it's okay with everybody. Are there any questions? Like, does anyone have any questions? My question is related to eigenvalues and eigenvectors. Algebraic multiplicity is the number of eigenvalues times number of times the eigenvalues repeat, whereas geometric multiplicity is the number of eigenvectors corresponding to a particular eigenvalue. For some matrix, we are getting geometric multiplicity equal to the algebraic multiplicity. For some matrix, we get geometric multiplicity less than algebraic multiplicity. Could you please elaborate this concept geometrically? A geometric multiplicity depends on the matrix element. So I'll take up this first question. See, first of all, the thing is like you consider any n by n matrix. You take A, let's say A n by n. I hope my screen is visible. Please let me know if there's any issue with the screen. So you take any matrix A n by n. Okay. Now what happens is if what you do is you just figure out the determinant of A minus lambda I or lambda I minus A, determinant of lambda I minus A is equal to 0. You do this, basically this is basically what we call as the characteristic equation. And what you do is you solve this characteristic equation. The roots of the characteristic equation corresponds to the eigenvalues. The roots correspond to eigenvalues of the matrix A, lambdas of the matrix A. Now, associated with the eigenvalues, you have what are called as eigenvectors, which are basically saying, look, these are the invariant vectors for that transformation for that matrix A, wherein which the scaling of the vector alone happens, the reorientation does not, what do you call, invariant with respect to the matrix A. So the only variation that you see is scaling. There is no orientation change or the direction change that happens. So now what happens is we want to figure out, there are two things that we need to figure out. We need to find out how many eigenvalues are there for a particular matrix A, and how many eigenvectors are there for a particular matrix A, right? So what happens is when you solve this characteristic equation, this characteristic equation will be an nth degree equation, right? Nth degree equation that you get. So naturally, you will expect n eigenvalues here, right? When you expect n eigenvalues, there are two things that we look at again. N eigenvalues, suppose if n is odd, that means you have, let's say, a 3 by 3 matrix or a 5 by 5 matrix or a 7 by 7 matrix and so on. One real value is guaranteed, real eigenvalue or real root is guaranteed. The rest of the n minus 1 eigenvalues can be complex conjugate pairs, right? And if you look at a matrix A of, let's say, degree uh, let's say, uh, even, of degree even, then you're going to have a problem. The problem is you are going to get complex eigenvalues. 1 minute, just a minute, just 1 minute, just 1 minute, just a minute, guys. Hello. Sorry, I had somebody at the door. Okay. So there can be complex eigenvalues for a square matrix of dimension even, and for a square matrix of odd dimension, you will at least be guaranteed one eigenvalue. So the second thing that we are worried about is, like, when you have linear equation, you will just have one root. When you have quadratic equation, wh- so when you have quadratic equations, there is a problem. The problem being the roots can be repeated roots, right? When you have repeated roots, now there is a question that comes into picture. If you have, let's say, eigenvalues which are distinct, each of those eigenvalues will actually have a corresponding eigenvector. Now, what happens is when the eigenvalue is repeated, we want to know what happens there. So we will say the number of times an eigenvalue repeats is basically called the uh, algebraic multiplicity. The number of times eigenvalue repeats is basically the algebraic multiplicity. And the number of eigenvectors associated with a particular eigenvalue, that is basically called the geometric multiplicity, right? The number of eigenvectors associated with an eigenvalue, associated with an eigenvalue. This is the geometric multiplicity. Now, it could be such that there might be cases wherein with the number of eigenvectors associated with the repeated eigenvalue could go less. Could go less in the sense we took this example. If you look at this 1 1, let's say 1 1 1 0, if I take this matrix, or probably let me take 1 1, okay, 1101. Let me take this matrix. So in this matrix, this is basically the shear matrix that we have, in which case the characteristic equation is basically lambda minus 1 the whole squared is equal to 0, which implies lambda is equal to 1. It is repeated twice, which means the algebraic multiplicity of 1 is equal to 2. Algebraic multiplicity
of lambda is equal to 1 is basically 2. When you try to find out what is the eigenvector associated with this, the only eigenvector associated with this would be 1, 0. You will not get a second eigenvector in this case, which means this eigenvalue, which is lambda is equal to 1 with algebraic multiplicity 2, we say is a deficient eigenvalue because it does not have two eigenvectors. So this is the one thing. This is what we are trying to say, that the algebraic multiplicity and geometric multiplicity, as far as that is concerned. However, when you look at, let us say, a repeated eigenvalue in 3 dimensions, suppose I take a matrix A, which is 3 by 3. If I take a matrix 3 by 3, then what happens? I may have, let's say, lambda 1 is equal to, say, 1. For a simple example, I am not considering a specific matrix. I'm just giving you an example. Lambda 1 is equal to 1. Let's say lambda 2 is equal to 2. And lambda 3 is also equal to 2. Now, we all know that if you take a 3 dimension, you can have the geometries, the linear geometries that we get. You can look at it as lines through the origin and planes through the origin, right? A plane is basically a 2-dimensional geometry which would require 2 linearly independent vectors to be spanning it, or to be forming this particular plane through which is passing through the origin. On the other hand, a line passing through the origin will require only one linearly independent vector to span that entire vector space. Therefore, when you look at a 3 by 3 matrix, a repeated eigenvalue has a facility wherein which it can have equal number of eigenvectors. For example, in this case, if you see lambda is equal to 2 is repeated twice. When I say lambda is equal to 2 repeated twice, all I'm looking for is I'm going to look at a minus 2i times x is equal to 0. That means I'm going to look at the null space of this matrix A minus 2i. This x corresponds to the null space. X belongs to the null space of A minus 2i. And when you have a 3 by 3 matrix, you do know that the null space of a matrix can be dimension 2, right? You can have dimension 2, a matrix to be of dimension, a 3 by 3 matrix, where the null space is, 2-dimensional, and the column space is 1-dimensional. We are only looking for rank plus null, the rank nullity theorem, where we say rank plus nullity is equal to 1. So in higher dimension, you will have geometry which would probably allow you. Suppose if I say, I take this matrix wherein which I have lambda is equal to, let's say, 3 repeated thrice. I take another matrix where lambda is equal to 3 repeated thrice. Then what does it mean? This simply means I'm looking for a minus 3i times x is equal to 0, the 0 vector. And this implies I'm again going to look at the null space of a minus 3i. This is second example. Now, the null space of a minus 3i. When I say null space of a minus 3i, and the thing is, the null space in this case cannot be a 3-dimensional space, because if you want to have a 3-dimensional space, a minus 3i itself should become a 0 matrix, completely 0 matrix. Is that clear? Of course, I can always look at the diagonal matrix with 3. So I will have a minus 3i to be completely a 0, a completely 0 matrix, in which case the null space is going to be dimension 3. All right? And that will not happen because the matrix that you are trying to find the eigenvalues and eigenvectors for will at least have one linearly independent vector, which means the rank is going to be 1. So there is a problem there. So that is exactly what we face here. It says for some matrix, we will get geometric multiplicity and algebraic multiplicity to be the same. For some matrix, the algebraic multiplicity could be higher than the geometric multiplicity. Therefore, what we say is the geometric multiplicity can at most be equal to the algebraic multiplicity. Suppose if there is an eigenvalue which is repeated, let's say twice, you cannot have a three eigen directions. Is that clear? That's what it means. Okay. I hope that is fine. If the person who asked the question is in the group or chat, you could tell me whether you are fine with this answer. The next question says in assignment 6, question number 5, what is the linear map given by 1, 0, 0, 0, 0, minus 1? This was actually a mistake. We have rectified that.
Hello, sir.
Yeah.
Sorry to interrupt you. Can I ask something from this part which you explained right now?
Yeah, Rohan, go ahead.
Uh, yes, sir. So, yeah, showed us two examples where AM is equal to GM, and when
Mhm.
AM is greater than GM, that repetition case. But
Yes.
we know one thing, that AM will always be greater than GM. Like, but intuitively, can you give me some example or some feelings? I don't feel it actually. I know the rigorous proof why AM is greater than equal to GM, but
Mhm.
can you give me some intuitive idea why the algebraic multiplicity should always be greater than geometric multiplicity?
So, okay. See the intuitively, if I were to say, all I want to, Rohan, can you mute yourself? Or Shivakumar sir, can you please mute yourself? Yeah. See, uh, can you please mute yourself, sir? So Rohan, it is this, like when you try to what do you call, when you try to solve a system of equation, when you solve a characteristic
Mhm.
equation of this, you only talk about the root. See, there is no question of intuition out there in terms of the eigen, what would you call, the eigen values, because you're just trying to solve the root of the equation. I'll come to an intuition at a later point of time, maybe on other discussion.
Okay,
But
okay.
you see,
Yes, sure, sir.
yeah, if you see, when you really look at solving your quadratic equation or the characteristic equation or any power, any degree equation, you end up getting roots for that equation. Is that correct? Now,
Yes, sir.
we'd have no control over the roots. It depends on what the matrix is and what the characteristic equation is. We will get that, right? And corresponding
Right.
to that is what we get the eigenvectors. We are only looking for those invariant directions for that particular matrix, which are basically scaled by the corresponding eigenvalues that you've found out. Is that clear?
Okay.
Are you getting it?
Yes, sir.
So
Yeah.
when I
Yeah, yeah, yeah.
have, so what happens is when I have, let us say, um, an n by n matrix where, let us say, I have an eigenvalue which is repeated, let's say, 3 times, right?
Mm-hmm.
What happens is in that n dimension, I would still be able to find a three-dimensional null space for this particular matrix A minus whatever 3 times I for that n by n matrix. Is that clear? So a higher
Right.
dimensional vector space where you're going to look for this eigenvectors, invariant subspaces A n by n for n greater than 2. What happens is
Mm-hmm.
you will still, the geometry will still allow you to look for, let us say, multiple eigenvectors for the same eigenvalue when it is repeated. Are you getting it? Precisely the example that I gave you corresponding to lambda is equal to 2 twice in a three-dimensional space. Are you getting it? Because I have a geometry which is the plane which is sitting out there. Is that clear? A plane passing through the origin would actually be a vector space. Is that correct? The entire plane, the entire set of vectors in that plane is going to be invariant under this transformation A. Are you getting this?
Right. Yeah, yeah, yeah. Up till this is clear.
Yeah. Yeah.
Yeah.
So now what happens is when beyond 2 dimension, when you go, you will have that what you call I wouldn't call it a degree of freedom. You will have that facility. The space renders, the space allows you to have accommodate with multiple eigenvectors for the same eigenvalue. Are you getting it?
Okay.
Uh, uh, Beyond that, if you go, see, only for 2 dimension you'll have this problem. And suppose I have an n by n
Mm-hmm.
matrix where I mean, this is exactly where I come to. You take this simple 2 by 2 matrix, which is 1001, diagonal matrix, right?
Right. Yeah.
The eigenvalues are basically one, repeated twice.
Yeah. Mm-hmm.
But that is also the identity transformation, which means the entire plane is going to be the eigenspace for it. Entire
Right.
xy plane you're going to have is going to be the eigenspace for it. The same is the
Mm-hmm.
case that will happen if you have, let us say, a 3 by 3 matrix where in which all the eigenvalues. Suppose I can take a diagonal matrix which is 3 0 0 0 3 0 0 3. Basically, all the
Mm-hmm.
eigenvalues are. In which case, you can say that the entire 3D space is going to be the eigenspace for this. Is that clear?
Okay. Yeah.
But suppose I take another matrix. Let's take the case like what we had here, 1101. In this case, there is a see, the constraint is the matrix is the constraint basically. When you have a diagonal matrix, your life is simple. In this case
Mm-hmm.
that I take 1101, even though I have lambda minus 1, the whole squared is equal to 0, and I get lambda is equal to 1 twice. When I solve a minus lambda x is equal, lambda I times x is equal to 0, I will end up, this matrix will come into picture, which is going to dictate how the eigenvectors are going to be, right? Because that's what you're going to look
Right.
at as null space. So
Mm-hmm.
this what do you call, the constraint is actually imposed by the matrix itself, number one. Is that clear? On whether you will have multiple eigenvectors associated with the repeated eigenvalue or not. Is that clear? That is why I took this second example, where in which I took one, there are two distinct eigenvalues, after which the second eigenvalue is repeated twice. Is that clear?
Yes.
In this case, if you see, you're going to have this matrix A minus 2i into x is equal to 0. This is what we're going to have, right? And it is repeated twice, we have told. Is that clear? If it is repeated twice, you look at A minus 2a, this rank of this matrix A minus 2a for a 3 by 3 matrix is not going to be rank 3 for A minus 2i into x. Is that correct? The rank is definitely not going to be 3, because you have said the determinant of A minus 2x is equal to 0. 2i is equal to 0.
Right.
Which means it is a rank deficient matrix. Is that clear? Now, if it is rank deficient matrix, that means the null space of that matrix, A minus 2i, that matrix that you have, null space of the matrix is going to be not a zero-dimensional null space. Are you getting it?
Right.
It won't be a zero. So it can only be either one-dimensional, two-dimensional, or three-dimensional subspace. Is that clear?
Yes.
The null space of it, right? Yeah. When I say it is repeated, it's going to be repeated twice. That means when I do this A minus 2i times x, I will find one linearly independent vector here. There will be two linearly dependent vectors in this case. Is that clear?
Yes.
Which means if that is the case, then the null space will become two-dimensional. Are you getting it? When will the null space be equal? When will the dimension of the null space be equal to the dimension of that matrix itself? Only when it is going to be zero matrix. Are you getting it? Zero matrix, if I take 0, 0, 0, 0, 0, 0, 0, 0, 0, it is a three-dimensional matrix, or it's a 3 by 3 matrix for which the null space is entire R3.
Yeah.
Because every vector is going to get transformed to zero vector. Is that clear?
Right.
So are you able to connect all these things and then figure out the answer for the question that you had? I'll take up the other question because otherwise we'll run out of time. Is that okay?
Okay, sure, sir. Yeah.
So I hope you'll be able to connect the dots for this and then figure out the answer. Is that clear? Yeah, I'm almost given.
Yes, sir.
Okay.
Yes, sir. I'll think of.
Sure. So this question number 2, it is already sorted out. The answer is basically, no, we have sorted it out. The answer is rotation about 90 degrees, rotation about x1 axis. It's not about reflection. That's the thing. Okay. Okay. So what is when lambda is equal to 3, we can get the null space of the vector is 3 linearly independent. That's what I told you just now. When the null space, when you have lambda is equal to 3, and you can actually make you can make a diagonal matrix. If it's a diagonal matrix with all the diagonal elements to be equal to 3, then you will get 3 linearly independent vectors. Suppose if I give you this, it's a good question, Mr. Perumal Swami. When lambda is equal to 3 repeated twice, we can get null space vector, which is 3 linearly independent vectors. Determinant of a minus 3 is this is wrong. If determinant of 3i a minus 3i is not equal to 0, determinant of a minus 3i will be equal to 0, because that is exactly how you got the eigenvalues. Is that clear? So this condition will not be there. If determinant of 3i a minus 3i is not equal to 0, that will never happen, because you started with the premise that determinant of a minus lambda is equal to 0, and you figured out lambda is equal to 3. Okay. Now, the second thing is, suppose if I take this upper triangular matrix, let's take this 3, 1, 1, 0, 3, 1, 0, 0, 3. I take this. Even for this matrix that I have, the eigenvalues will be 3, 3, 3. But then you will not get 3 linearly independent vectors here, and therefore it will not span the entire 3D. This is exactly the problem that we had here. It is defined by the matrix, the number of the number of eigenvectors corresponding to repeated eigenvalues. It is determined by the matrix. Okay. Any other question? Can we have? Are there any questions? Are there any questions that are being posted? Yeah.
Sir, I joined 1 or 2 minutes late, I think. So where are you referring these questions from? So I cannot see any questions pool or some.
No,
where are you referring these questions from?
The questions are basically either put in the chat box of this Zoom meeting, or I think people are posting it on YouTube, and that's being copied and pasted here.
Oh, okay.
Yeah.
Sir, I have one doubt. May I?
Yes, Rohan.
So, in a very recent quiz, it was asked that I think quiz 11 or something. Property of a projection matrix. So, projection matrix is always idempotent. I agree with this. But is it always Is it necessarily be symmetric?
100%. 100%. Projection, the properties of projection matrix itself, it is symmetric matrix. I'll tell you, how do you get, suppose I get you this. I have a vector U, and I want to find out the matrix that projects, that matrix which projects every vector into the direction of U. Every vector on to the direction of U or in the direction of U. How do we get this? Direction of U. So that matrix, let me call that as A subscript U, to say that the matrix is A generated by the matrix generated, or the matrix that is going to project all the vectors in the direction of U is going to be given by U transpose divided by U transpose U. This is the matrix that I have. Is that correct, Rohan?
But sir, this case will only arise if you are taking orthogonal projection.
And
Otherwise,
I'm just
you
taking a
won't
single
be getting
vector.
this.
I'm only talking about orthogonal projections, right? What are projections that we're talking about is all orthogonal projections, not some oblique projection or something. When you look at orthogonal projections, the projection matrices will always be symmetric and idempotent. It is a property. Now, if you take A transpose,
Right.
A transpose is again U transpose by U transpose U.
Yes, sir, that I agree. I was thinking about like projection in general terms.
No, the definition of an orthogonal projection matrix, the definition of the projection matrix itself is a matrix which is symmetric and idempotent.
Right, sir. Yeah, for orthogonal matrix, it's right. So actually, in the question, nowhere it is mentioned.
Which one? We have not done oblique projection or anything in the course. We have done only orthogonal projection. Is that clear? So, what we have done is what we ask our questions. We don't ask something which we have not done, right? Maybe problem solving we would have given, but we have not even talked about oblique projections anywhere inside in the course throughout. So whatever projection, see, you cannot be reading between lines. Okay, don't do that. Because you start reading between lines and then every word, then there's going to be a serious issue, right? Don't do that.
Okay, sir. Yeah.
No issues. Yeah. Any other question, or are there any questions? Kavya, Aditya, do you see any other questions? There are no questions. Is there any other thing that you want me to clarify your doubts or anything? There are many people who are here, but I don't see them asking questions. Hello? Hello? So let's look at, in that case, let's start with assignments and then check quickly the answers for the assignments. I hope that would be fine. Lecture number 6. I think we can go till 10 if I'm not wrong. 11 and 12 I'll not be able to give now. Till 10 we'll have. See, there are places where if there are any option mistakes which we have found or which have been brought to our notice, we have already informed the backend team of NPTEL. They would have corrected the answer, or they would have not evaluated that particular question. You wouldn't be given marks for that question, and it will be that question is taken out of evaluation. Is that clear? So you don't really have to worry about the marks and scores. If there are some 1 or 2 questions where it has not been done, it would be taken care before we finalize before you go for your exam. So you don't have to worry about it. Okay. So assignment 6, week 6, assignment 6, it says let T be R3 to R3 linear map with matrix 2, 0, 0, 0, 3, 0, 0, 0, 4. If T acts on a cube of side 1, then the volume of the transformed cube, what is the answer? It is basically the determinant of this matrix multiplying the determinant of that other matrix of cube side 1. Cube side 1 will have volume to be 1. So the determinant is going to be 2 into 3 into 4, which is 24. So the answer is 24 in this case. Then the determinant.
Sir, your screen is not visible. Can you make us also see the screen so it will be easier for us to follow along with you?
I'm showing the assignment 6, so if you can open it on the SWIME portal, it will be good.
Okay.
Yeah, I'm taking it from SWIME portal only. Okay.
Okay.
Yeah. So that is the answer. Then the determinant of a 3 by 3 matrix representing a linear transformation R3 gives the scaling factor of area, scaling factor of volumes, one for any transformation, the trace of the transformation. So always determinant of a 3 by 3 matrix will give you volume. So this basically talks about scaling of the volume. Okay. This always talks about the scaling of the volume. And 1 minute. The third question says determinant of a 3 by 3 matrix whose columns are UVW is equal to, how do you express it as the triple product of vectors? You have this U dot V cross W, the volume of the parallelepiped formed by UVW. See, UUW, so that option is wrong. The answer is option B, which is U dot V cross W. V cross W, we have already seen in case of 2 by 2, it's the area of the parallelogram. And V cross W will be in the direction of U because the cross product is basically a vector which is orthogonal to both the vectors. So it will be the direction of U. Now you'll have U dot U, which is going to give you a number, and that's going to be the volume of the parallelepiped. Then the linear transformation R3 has eigenvalues 2, -1, and 0.5, the volume scaling factor. This also everybody knows because the determinant of the matrix is equal to the product of the eigenvalues. So this would be 2 into 0.51, 1 into -1. So the answer is -1. Then the eigenvalues of the reflection matrix are always 1 or always -1 or plus or minus 1, have at least 1 0. Reflection matrix, you must know that reflection will not change the shape or what would you call it, not change the length. Therefore, reflection, the matrices, the eigenvalues of the matrix will always be plus or minus 1. So 5, the answer is plus or minus 1. Then if there is a linear map R3 that doubles length along one eigenvector, triple along the other, and reverses the direction in the third value while keeping its magnitude unchanged, then the determinant is, that means it says the eigenvalues are basically 2, 3, and then a -1. So 2 into 3, 6 into -1 is -6. Then let T be a shear transformation in R3, which of the following is true? Here the answer is determinant of 1. Determinant is equal to 1 always. This is basically an elementary shear transformation that was talked about. And I think there were some issues when people had raised it, which we sorted it out for this particular question. Then if A is a diagonalizable matrix with eigenvalues 2, 3, 4, then the volume of the unit cube under the transformation A squared. So A squared will be, you take the product of this 2 into 3, 4, 6 into 4, 24. So 24 square, which is 576. Then the trace of the 3 by 3 matrix is equal to the sum of its eigenvalues. So it's counting the multiplicity. So you just add the eigenvalues, that's going to give the trace of the matrix. If a linear transformation R3 has eigenvalues 1, 1, and -1, which are the statement is true, it's pure rotation. It reverses orientation, preserves volume. It's a pure shear. It preserves volume but applies shearing. So basically, there is an orientation change here with -1. So it reverses orientation, but the volume is basically preserved. The unit cube, the volume is going to be, see, if you take the volume, it's going to be 1 into 1 into -1. So it's -1. So magnitude is remaining the same, but the direction is changed. Consider the following statements regarding transformation in R3. Shear transformation matrix, positive eigenvalues. Rotation matrix about x-axis has at least one eigenvalue to be equal to 0. The product of magnitude of eigenvalues of rotation matrix is unity. So if you look at what are the current statements, so shearing transformation always has positive eigenvalues. I think these things we have covered in the lecture. And the product of magnitude of eigenvalues of rotation matrix is always unity because rotation will not change anything. So the volume, the rotation matrix, if you take the determinant, it's going to be unit because it's a rigid body rotation. So it's not going to change anything. So that's the answer. Then you have the columns of the 3 by 3 matrix are given to be 1, 0, 2, 2, 1, 1, and 3, 4K. If the absolute value of the volume of the parallelepiped is 10, then the two possible values of K, this you have to work out and then check, and you will get the answer to be K is equal to 4 and -16. I'm quite sure many of you have answered this. I've checked this also. Then if the linear transformation in R3 maps every sphere to an ellipsoid, then the transformation must be orthogonal, invertible, can have determinant 0, and is necessarily a projection. So it says it maps every sphere to an ellipsoid. So you take it as then the answer is going to be invertible transformation. That means you can go forward and come back. Which of them are following shear matrix? There was a huge discussion about this question also in the forum. ABC that maps to the vector 0, 0, C. How can this be a shear and all? I think Rohan answered this question. So the answer here is minus C by A, C by B, minus C by B, and 1. That would convert. That would basically act as a shear transformation on this vector to get 0, 0, C. Then the 15th question is, there's a linear map given by this. What does it do? There was a problem here. We changed the answers. The answer is going to be rotation by 90 degrees about x1 axis. Then the 16th question is linear transformation R3 to R3 has matrix, it says A5. It is known that two eigenvalues are 2 and minus 1, and the corresponding eigenvectors are orthogonal. If T maps a cube of side S to a parallelepiped of volume 64, what is the volume of what is the absolute value of S? So we really have to find out what is, in this case, you already know that the what do you call, the eigenvalues are 2 minus 1, two of the eigenvalues are 2 and minus 1. Trace is given to be 5, so 2 plus minus 1 plus x is equal to 5. So x will be equal to, this is x plus 1 is equal to 4, x plus, yeah, 2 minus 1 is 1. So x plus 1 is equal to 5. So x is equal to 4 you get. Now you want to look at the T maps a cube of side S to a parallelepiped of volume 64. What is the absolute value of yes? So you're basically trying to figure out what is the side of the cube. So that will work out to be 2. So that completes assignment 6. Are there any questions? Are there any questions on the? Thanks a lot. Thanks for your comment. I think it's you basically try to do it in a very, very intuitive way. And when you do it intuitive, you also show the geometry. See, normally what happens is, whenever math is done, if you do it intuitively, and especially in ideas like where geometry is involved, if you can show the geometry and do, I personally believe that conceptually you keep building, your equations will actually come to you saying, look, this is the equation that has to be there. There's no other reason, that there cannot be any other equation other than what we have to put it there. So it's always nice to look at it, that way. So I hope, till what time should we go ahead? 3:30, right? NPTEL teen people?
3:45, sir.
Till 3:45, so I still have time. So the next one is at 4 o'clock, right?
Yes, sir.
Okay, great. So that's there. Any specific question that you guys want me to address, or what is it like? Is there any question or any concept that you want me to recap, or what would you call, help you do it now? Then I can actually do it. Otherwise, we'll go ahead looking at the assignments again. Hello? Do you guys have any questions that you want me to discuss, or concepts that you want me to discuss?
No, sir, nothing specific from my side. Further, sir, please mention.
Yeah. That's the case. If it's not there, then I would probably go ahead with the assignments. So 6 we have done. Let me check 7. And there were a couple of assignments where there were mistakes. See, one thing is like we had certain issues with the interface where, like, we fix the thing and then come back by mistake. You click the other option gets clicked and that gets saved. And since we had put the option correctly, we would have felt that, okay, this is the correct option we have put. Why is it showing a different option? And that is one thing. And second thing is, like, yeah, there could have been a typographical error also. Those things were sorted out. If there are some issues in which it was not sorted out, please bring it to my notice. on the forum that we have, we'll do it. Okay, week 7, question 7, week 7 assignment. It says consider the system of equations in R3. X plus y plus z is equal to 1, 2x plus 3y plus 2z is equal to 2, 3x plus 4y plus 3z is equal to 3. Which of the following is true? The system has unique solution, infinitely many solution, inconsistent, and system reduces to one equation in 3 variables. So if you, I would suggest that you do the determinant for this, or probably root the row reduced echelon form and find the rank of the matrix. Once you find it, you basically see that this system will have infinitely many number of solutions. Then the second question is, a homogeneous linear system has Ax equals 0 in R3, has a two-dimensional solution space. Then which must be true? So the null space basically is a two-dimensional subspace of R3, in which case you have to now look at what is the rank of the matrix. So which of the following is true? It says determinant of A is not equal to 0 is not an option because the homogeneous system of equation has two-dimensional subspace. Nullity of 1 is ruled out because, again, it's a two-dimensional subspace, therefore nullity has to be 2. A cannot be invertible because you already have a non-zero solution to Ax equal to 0. So the only option that you have is rank of A is equal to 1. So if A is equal to LU, then the LU decomposition of 3 by 3 non-singular matrix, which of the following is correct? L is always unique, U is always unique. Both L and U are unique if we impose unit diagonal entries on L. LU decomposition always exists without row exchanges. That is not correct. The only answer is like both L and U are unique if we impose unit diagonal entries on L, because when you look at multiplication, what happens to the diagonal elements, you will see that L has to take unit values so that the diagonal elements are sorted out. Okay. Then suppose A is equal to 0, 1, 1, 1, 1, 0, 1, 0, 1, which of the following is true with regarding to the LU decomposition without pivoting. So you can do LU exists without pivoting. LU does not exist without row exchanges. LU decomposition is unique without pivoting. And LU decomposition always requires L to be orthogonal. This L to be orthogonal is not something we need. Only thing that we need here is, you see that the first element of the first row is a 1. Therefore, the first element, if you want to do the, if you actually get into your A matrix where you have L into U, the leading element being 1, then you have to do rows, row swap. So it says LU decomposition does not exist without row exchanges. That means you need to do row exchanges, otherwise this pivot element being 0 will cause a problem. Division by 0 will be there and it will cause a problem. If A is m by n matrix with m greater than n and rank of A is n, then the least square solutions of x is equal to x hat is equal to x equal to, of x ax equal to b satisfies A transpose AX hat is equal to A transpose B, A transpose X hat is equal to AB, AX hat is equal to B exactly, X hat is unique only if M is equal to N. This is basically the problem of least square solution itself. So you have A transpose AX, the whole hat, the A transpose AX hat is equal to A transpose B. This is a problem which we have done, which is straight from the lecture. So the answer is option A. Then let X hat be the least square solution to X equal to B, which of the following statements is false? Least squares always minimize Ax minus B the whole square. The residual vector RB is equal to A minus Ax is orthogonal to the column space of A. If A is a full column matrix, then X hat is equal to A transpose A, the whole inverse A transpose B. And if A is not a full column rank, then least squares has no solution. See, the entire idea is, if you don't have a solution, you at least look for least square solution. Least square solution will always exist, and therefore this last statement is incorrect statement. That's the false statement. Then you have U is equal to U transpose ME, where M is equal to this, which of the statement is correct. It's not an inner product because M is not symmetric. This is an inner product because M is symmetric and positive definite. This is actually a property of this positive definite matrix, where you're going to define this. The inner product itself is to be like this. And this is not an inner product because M is singular, and M is not singular because the determinant of this matrix is not 0. This is an inner product if only restricted to R2. You can't even do that. That is wrong. So the answer is, this is an inner product because M is symmetric, positive, definite. Then for two vectors U and B, the Cauchy-Schwarz inequality in an inner product space guarantees This is basically with that less than or equal to thing. So it's basically says u comma v, the inner product of uv the whole square is less than or equal to u square into v square. Then you have Gram-Schmidt applied to the vectors v1, v2, v3. If one of the vectors lies in the span of the other, then what happens is all three orthonormal vectors can still be produced. Only two will be produced. The process fails entirely. The resulting has dimension 3. If this see since v2 lies in the span of v1, you will get only one vector for that, and the other vector is v3. So corresponding that you will get an orthonormal vector. So you get two orthonormal vectors. So that's the answer. Question 10, applying Gram-Schmidt to the set of 110, 101, 011 in R3 will yield. If you look at this 110, 101, and 011, these three are basically linearly independent vectors. So you will get an orthonormal basis for R3 from here. Which of the following is true about QR decomposition? A is equal to QR square invertible matrix of dimension 3 by 3. Q is orthogonal, R is upper triangular. Q is upper triangular. This is all like some bakwas options that you've been given. QR, you already know that Q is always orthogonal, and R is upper triangular. Then if A is m by n with m greater than n and full column rank, then its QR decomposition A is equal to QR is a square n by n upper triangular matrix and invertible, square m by m orthogonal, rectangular with more rows than column, always diagonal. So this is going to be what do you call it's going to be a square. R is going to be a square n by n upper triangular matrix. So you're talking about R. R is always an upper triangular matrix. And when you say upper triangular matrix, it will be a square matrix. So you're going to talk about square matrix of dimension n by n. Okay. Then for the matrix 2, 0, 0, 0, 3, 4, 0, 4, 3, which is true. I mean, you have to do the computation here and figure out that the eigenvalues are 2, 7, and -1. Then you have this matrix E, which is 0, 0, 1, 0, 1, 0, 1, 0, 0. Swap the first component with the third component, the inverse of E. The inverse of E will be the matrix itself, right? It is going to swap. It's going to do, this is basically a reflection in x1, x3 plane. X2 component is fixed. So the inverse will also be the same. So the matrix is the same. If Q is orthogonal matrix, which of the following is not necessarily true always? Q transpose Qj is 0. I and J are different columns. That is true because they are orthogonal. Qi transpose Qi is 1 because that's the length of the column unit vector. Then Q transpose Q is equal to n by n identity matrix. That is true. Determinant of Q is 1. So this Q, the determinant of Q is equal to 1 is not guaranteed because Q matrix can actually be a rectangular matrix, in which case determinant is not defined. Is that okay? So that I think.
Sir, I think
yeah.
Q can also have data as -1, and
No, but
that's why.
No, the point is it's not about -1. First of all, determinant may not even exist.
But you're saying orthogonal matrix, right?
Orthogonal matrix. I can have two columns which are orthogonal to each other. A 2 by 3, a 3 by 2 matrix I can have which are orthogonal to each other.
Right. But that won't be called an orthogonal matrix by definition. So
It will-
orthogonal matrices are by definition square.
No, orthogonal matrices are matrices with unit vectors, column vectors, and column vectors being orthogonal to each other. That's the definition of orthogonal matrix. Okay.
Okay, sir. Actually, Gilbert Strang in his book wrote that there's a problem. There's a misnomer actually with this orthogonal and orthonormal matrices. It would have been best defined by some other name, but the situation arose like this that everyone called this orthogonal matrix.
Orthogonal matrix,
So,
the definition, if you put an orthogonal matrix, the definition is Qi transpose Qj is equal to 0 if I is not equal to j, is equal to 1 if I is equal to j. That's the definition. Where Qi and Qj are columns of the matrix A. That's the definition. Okay.
okay, sir. Okay.
Okay. Let's go to week number 8. Are there any questions in this? Week number 8. Can you explain question 12 in which assignment, sir? In the same assignment, is it week number 7? Assignment 9. I'm just going to assignment 8 now, sir. I'll finish it and then I'll go to assignment 9. Okay. Assignment 9, in fact, I think it had a couple of issues. I'll just check what it is. Okay. Assignment 8, week 8. Which of the following is a vector space over R? This is by the definition you have to look at it. So it says set of all positive real numbers with usual addition and multiplication, scalar multiplication, the set of all 2 by 2 real matrices under matrix addition and scalar multiplication, set of all non-zero real vectors in R3, then set of all real numbers with multiplication as the vector addition. The 1, 3, and 4 options will not work. When you take positive real numbers alone, you will have a problem because you want to look at getting a zero vector out of it. You need an A plus minus A. And that will be a problem. It's not there in that, so you'll have this issue. Only thing is set of 2 by 2 matrices will be under usual matrix addition and scalar multiplication will be vector space. Then you have U is equal to the span of 2 vectors. Then V is the span of another 2 vectors. Consider U union W. Which of the following is true? U union W. This was actually, I think this also was brought to our notice. It says U union W is a subspace only if U is a subspace of W or W is a subspace of U. In this case, you will see that it's not even happening because the first vector in U is going to be spanning the x1, x2 plane, and the second vector is going to span the x2, x3 plane. And if you look at W is going to span the x1, x3 plane, and the second vector is going to span the x3, x4 plane. So you will not have them to be a subset. So this question, the option is wrong. So we have actually, so it's basically U union W is never a subspace of R. I think Rohan brought this to our notice. We've also informed the backend team for this. The dimension of the vector space of all polynomials of degree at most 4. This we must know. A polynomial vector space of, let's say, uh, at most degree n will always have n plus 1 linearly independent vectors because you have to accommodate for the constant term. Nth degree polynomial, if you take with the constant term, will have n plus 1 terms. So the basis is going to have the n plus 1 linearly independent vectors, and therefore the dimension is 5. The vectors 1, 0, 1 and 0, 1, 1 and 1, 1, 2 in R3, they are all linearly independent, linearly dependent, and form a basis of R3 and are orthogonal. I mean, if you add the first 2 vectors, you get the third vector. So you basically say that they are linearly dependent. Which of the following sets form a basis of R2? 1, 0, 0, 1, 2, 2, 3, 3, 1, 2, 2, 4, 1, 0, 0, 0. Except the first one, all others are like dependent fellows, so we'll not have going to be the basis. The span of 1, 1, 0 and 2, 2, 0 is basically all of R3, a line through origin in R3, a plane through origin in R3, 0 vector only. These 2 vectors are in the same direction, therefore it will be the basis will be, the vector space will be, or the span will be the line passing through the origin. The intersection of 2 subspace is always a subspace, a line, plane, then the 0 vector only. The intersection of 2 subspaces is always a vector space because you'll have 0 vector to be sitting in there. Okay. Then question number 8, the vector space P2 of all polynomials of degree 2 at most has dimension 2 basis 1x, dimension 3 basis 1x x squared, dimension 2 basis x squared. As we said before, this will have dimension 3 and the basis will have 3 vectors, which is 1x x squared. Then if V and W are subspaces of Rn, then dimensions of W plus V is equal to what? This is a good question. Unless they are orthogonal subspaces, V and W cannot, the dimension of V and W will not add up to dimension of Rn. So dimension of V plus W is dimension of V plus dimension of W minus dimension of V minus V intersection W. Which of the following is not a vector space? Set of all 2 by 2 symmetric matrices, set of all polynomials of degree at most 3, all continuous real valued functions 0, 1, set of all 2 by 2 invertible matrices. This 2 by 2 invertible matrices will have a problem because this set will not contain the 0 vector, therefore this is not a vector space. Which of the following sets is not a subspace of dimension R3? This also, I think, we had a problem. The second option is also not a subspace. The last option is not a subspace, so we have actually requested this question be pulled out. Question number 12. The vectors 1, 0, 0, 0, 1, 0 and 1, 1, 0 form a basis for R3, linearly independent, but not a basis of R3, span a line in R3. So 1, 0, 0, 0, 1, 0, if you add, you will already get 1, 1, 0. Therefore, the third vector is the sum of two vectors, so they are linearly dependent. Consider P3, the vector space of all real polynomials of degree at most 3, which was following is not a basis for P3. This you have to actually work out and check. And other thing is you can actually see in, what do you call? In all the cases, there are only, what do you call? You have to work out this problem. So the answer you'll get is 1 plus x plus x square plus x cube, 1 plus x cube, right? Then consider the vector space R3, V is equal to R3, which among the following is not a subspace of this one. The intersection of any two vector subspaces, it will naturally be a subspace. Every plane passing through the origin will be a subspace. I do not know the last option because this does not show up here. Every line need not be a subspace because the requirement is the line must pass through the origin for it to be a subspace. Okay. I will just answer this question. So just a minute. Let me finish this and then get back to your question. Then question number 15. Consider the following subspaces of R3, where the sum of all three guys is going to be 0. It's a three-component vector. Sum of all three components is 0. So if you say u1 plus u2 plus u3 is equal to 0, you can write u1 is equal to minus u2 minus u3. So you'll get you'll get two linearly independent vectors. Therefore, the dimension is basically 2 here. So questions, what's the question number 12? I think I will, I'll just check this once. Question number 12 of week 7. Question number 12. Column full rank, then R, it's about R. So the M by N, if A matrix is M by N, Q will take the dimension M by N. R will take a dimension N by N, okay? I think that's where the confusion is. I think I will stop with this because I have to sit for another course of mine. I have this live session. If there are any other questions, I would be more than willing to answer if you tell me, or any other comments that you have. And I would also thank all the participants of this course, both who have taken up the exams and the ones who have just registered for the course and have gone through all the assignments, the contents, the videos and all, and who brought out the silly mistakes that I would have done in terms of, let's say, making instead of R2, I would have made R1, or instead of A22, I might have made A21. There are many people who have posted the comments also. I'm really thankful to all of you for actively participating, and especially Rohan, I want to thank, because Rohan Biswas seemed to have done a lot of answering on the forum, which made the forum also lively in the sense any doubts that were asked even before I could get on, or my TAs could get on and give the answers. Rohan was already there giving the answers. It was all good. And any place where it required my intervention, I'd posted the answers and stuff. I hope you all found the course to be really useful, worthy 40 or 30 hours of time that you spent. And I also hope you never felt bad about the extra stretching that we did in most of our lectures. Instead of 30 minutes, we would have we would have done like 40 minutes, 45 minutes or so. That's because when we get into the mode of giving explanation and intuition, we want to go to that extent where we actually create some kind of curiosity and then lead to the next class. So till that point, we wanted to continue. It's not like we bring in something preset kind of notes and then say we stop with this, therefore we'll go to the next one. We don't really, we were not doing that. And we felt, as we were teaching, there were some questions which came to us which we felt must be answered, and that's exactly how we carried out over the entire course itself. So if any of you had found it to be a bit overkill, I'm really sorry to that extent where, it was not crisp, it was a bit more elaborate. But for all the others who found the course to be useful, I really thank you for all the feedback, the comments that you put on YouTube videos and as well as on the forum. I thank you all. This time, I must say, I had full support from my TS Kavya and Suhas, who were coming out with some interesting questions, and then we had to brainstorm a lot of questions. See, that's also one place where the answers could have got flipped a bit. So, but I think I thank all my TAs for this course, and of course, previous Gaurav Hegde, who ended up making all the beautiful illustrations that you'd have seen on the video. And of course, I'll also thank my co-instructors, Mr. Krishna Kumar and Dr. Ashok Rao, and all the NPTEL team, backend team here in IISc, and also the IIT Madras team for having allowed us to, kind of change the, incorporate the corrections and change the lectures and, editing and other things. I thank IIT Madras team also. I also thank our IASC NPTEL chairman, Professor Rumanan, who gave us permission to this. And it was really wonderful interacting with all of you and knowing all of you. And thanks a lot for your support in terms of your comments. And thanks a lot in terms of your feedback and the forum questions. It also helped us to learn a lot, especially when Rohan put something. I used to go back and say, okay, fine, this guy is saying something. I had to go and check whether this is correct or how do I intuitively put that. So it was really a wonderful experience that I had. I hope you guys also found your time to be properly utilized as far this course is concerned. It was not a waste of time. So thanks a lot, guys. We will meet or we will discuss on our forum in Google. We'll continue to discuss in this forum and probably we will carry on with our discussions. Thanks a lot to all of you and all the best for your exams. Do well. Ashok, sir, do you want to say a few words, sir? Professor Ashok Rao is also here.
As long as they've enjoyed the course, it's fine. They will learn something down the line. Instead of worrying about exams, I hope they spend more energy on enjoying the course. That's
Yes, sir.
okay. Yeah.
Yeah. Thank you, sir. Thanks a lot. So thanks a lot to all of you. We'll get ready for the next one more